Welcome back to Science Unpacked. Today, we're diving into some fascinating green chemistry, specifically a paper by Sachin Jalwal and team.
Yes, and it's all about making a really useful chemical called formate, but in a much more sustainable way. It's truly exciting stuff.
The paper is titled Manning's Catalyzed Formate Synthesis via Coupled Methanol Dehydrogenation and Bicarbonate Reduction. Quite a mouthful, right?
It is, but the core idea is brilliant. Formate is used everywhere, from food additives to a potential hydrogen storage material. It's a big deal.
Exactly. And traditionally, making formate involves harsh conditions and harmful chemicals like carbon monoxide. Not very eco friendly.
So these researchers are looking for a greener path, using readily available materials like methanol and bicarbonate. That's where the innovation lies.
They're using a special type of catalyst, a manganese based complex they call Mn1. Manganese is an earth abundant metal, much cheaper than rare ones.
That's a huge plus for scalability, isn't it? Using common metals makes these processes more viable for industrial use in the long run.
Absolutely. The reaction itself is quite clever. It's a coupled process, meaning two reactions happen together.
So, methanol gets dehydrogenated, releasing hydrogen gas. And then that hydrogen helps reduce bicarbonate into formate. It's like a chemical dance.
Precisely. And a byproduct of methanol dehydrogenation, formaldehyde, also gets converted into formate. So, less waste, more product.
That's fantastic. They achieved a turnover number, or TON, of up to 2630. For our listeners, what does a high TON mean?
A high TON means the catalyst can perform its job many times before it deactivates. So, a small amount of catalyst can make a large amount of product.
That's really efficient then. And they found that using potassium bicarbonate and KOH worked best, right?
Yes, the potassium salts improved efficiency significantly. They also did a cool experiment using 1,3C labeling to trace where the formate came from.
Oh, like putting a tiny tracker on the atoms. What did they discover about the formate's origin?
They found that 76% of the formate came from the methanol and 24% from the bicarbonate. So both sources contribute, which is a key insight.
That's a dual pathway. It's not just one route, but a combination. Did they also look into how the catalyst actually works, step by step?
They did, using both experiments and computational studies, they identified the active form of the catalyst and the rate determining step.
And what about that formaldehyde byproduct? How does it turn into formate?
It can go through a Cannizzaro reaction, a metal-free pathway, or a metal-assisted one. The Cannizzaro path is quite kinetically accessible, actually.
So nature has its own way of doing it too, even without the catalyst. That's pretty neat. What about the effect of CO2?
Interestingly, too much CO2 can actually suppress the methanol dehydrogenation. It forms a stable, inactive complex with the catalyst, taking it out of action.
Ah, so there's an optimal balance. It's not always more is better in chemistry, is it?
Exactly. They also confirm the importance of the catalyst structure, particularly a specific NH group for its metal ligand cooperativity.
So the catalyst and its surrounding parts work as a team, almost like a tiny factory, to make the reaction happen efficiently.
Precisely. And a valuable byproduct of this whole process is hydrogen gas, which is a clean energy source.
That's a double win for sustainability, producing a useful chemical and clean fuel simultaneously. It's a fantastic step forward for green chemistry.
Though they note that methanol conversion is still low and bicarbonate reduction could be more efficient. So there's room for improvement.
But it's a solid foundation. This research really highlights how innovative catalyst design can tackle big environmental challenges. It gives me hope for a greener future.